Does infer that I wrote the STL, which I didn't. Obviously the talk is about STL, and there's a good quote from the author of STL, Alexander Stepanov, which will, I guess, be the theme of the rest of the next 40 odd minutes. Generic programming is based on finding the most abstract representations for efficient algorithms. So we're going to cover an introduction to STL and then an overview of the architecture of the STL, how the STL was implemented over 15 odd years ago, how we would use the STL, how we shouldn't use the STL, how we use it at SHE, and some exercises and some references at the end, which I hope that at least some of you will look at. There is some interesting reading in the references. So, the STL is a result of a bacterial infection. That's a direct quote from the man himself, and it's not really important to the talk. However, he had these ideas in his head for a number of years, and he couldn't figure out how to implement those ideas in the languages and technologies that were surrounding him. He ate some bad fish in the Ukraine and developed meningococcal or something. He was in bed for 6 weeks with high fevers and delirious, and during those 6 weeks he developed the core ideas that he spent the next 10 years trying to figure out. So, what is the standard template library? Created by Alexander Stepanov in the early part of the late last century or something. One key point about STL, which I think is missed, we work around it, we use it, and we use these ideas, but the key thing to me about STL is that it introduces the ideas of concepts as a concept, not as the general term concept. We know what concept means, but it introduces a concrete, abstract concept. I'll get into what I mean about concepts and models, but to me this is one of the key benefits of STL. The STL consists of various components that are largely orthogonal to each other, but they work together to provide the overall library. Those components can be broken down into containers, iterators, algorithms, and functional things. I've debated within myself how to call that last thing, like what is functional. I mean, there are things in programming that are not object-oriented. People tend to get carried away with object-oriented programming or generic programming. There are things that just do things. That's all they do, they just exist, they do one thing.
They call them functors.
Functors. But there's also, within that, there's the idea of carrying and binding arguments, and so that whole group of stuff I've just put under the banner of functional, and I'll cover these 4 areas. One thing that STL gives us that a lot of other libraries don't give us are complexity guarantees, and I'll cover what that means in more detail. But basically, when you use a component of the STL, you know what it's going to cost you. And in general, and in spirit with Bjarne Stroustrup's original intention, you don't pay for what you don't use. The other thing that the STL is it provides a framework that you can build on yourself. We'll have a look at that in the exercises. And another thing that the STL is not broken. It was created, like I said, 15 odd years ago, and there haven't been any patches to it. It's a large body of work in comparison to C++. I mean, C++ isn't a library, this is, but in terms of the specifications for it, it's similar in complexity, and yet it hasn't been changed. You don't see version 0.1a or 0.11b of STL, so you can have faith that it's pretty solid. And the caveat to that is if you think that STL behaviour is wrong, then it's more likely that you are in fact wrong and using it incorrectly. Now what I won't do in this talk is focus on a lot of little gotchas, here's what to do, here's what not to do. Of course I'll be pointing out some obvious ones, but I really recommend that you have a look at some material such as Scott Myers, of course, Effective STL, editions 1, 2 and 3, More Effective STL, Super Efficient Effects. Yeah, I had a quick look in the library. I think people might be having them around, but you should have them in the studio. There are links to PDF versions of those at the end. So, Alexander Stepanov, one of my personal heroes, believe it or not. He's got some fantastic quotes, and there is some material on him, interviews with him on the net. He's a very pretty, like a lot of people like him, Strustrup and Stepanov and the .NET guy, they don't give a lot of interviews, so I think he's got 3 or 4 that are available, worthwhile reading. Saying that everything is an object is saying nothing at all is a good quote, and people get caught up in genericity and they want to make the most general things, and they want to make, oh, if it's just an object then we can treat it like this, like every other object. And, well, sometimes you need to have distinguishments. Characteristic differences between things should also be recognised, not just searching for their similarities. And obligatory Wikipedia rip-off. Interesting from that is he's still very active. I sort of tend to think of Stepanov, if they think of him more, if they think of him at all, associated purely with STL. He's actually been around the traps for some time, and he's doing a lot of work currently, and very active at Adobe. Adobe's got their own template libraries, which are architected by Stepanov. Worth looking at as well. It's all open source. It's just good read.
Better just keep it ticking off as well, nothing together.
There is indeed. It's only 40 odd slides. So, genericity. A goal of the STL was to write down basic and common algorithms. The goal was to write them down once, so that they were done once and correctly, and they wouldn't have to be done again. So you could say once and for all that the minimum of 2 values uses these operators. And the focus on STL and the algorithms and the containers is throughout that all it's on the operators. You'll see a recurring theme that operators are important, not objects. And a key way that genericity was accomplished in STL was to abstract the storage so that you could use different storage mechanisms but access them in a common way via the idea of iterators. He was annoyed that programmers were still writing quicksort for the nth time, bubble sort, merge sort, all the different sorting algorithms, and writing them again. They've got a different container, they've got to write their sort algorithm again. He wanted to find a way that said, okay, here's quicksort, and it'll work for whatever container you give it. He tried it in different systems and couldn't get it really to work the way he wanted, and saw that C++'s templates were a close approximation, and argued with the creator of C++ to make whatever modifications were necessary to enable him to express what he needed to do using C++. So in some ways STL did actually influence the evolution of C++. A quote from Alexander: "You select different algorithms depending on the complexity of the fundamental operations provided by the data structure. You don't want to confuse disk and tape, even though they're functionally equivalent. They're inherently got different characteristics. You should write your algorithms that match well with the containers that you use, and if they're not, then change your containers or your algorithms." On the idea of performance, Stepanov knew that he had to show that what he'd written was provably correct in a mathematical sense, and that it only used, when it says it's log n complexity, it had to actually be log n complexity. We'll get into complexity guarantees as well. But he knew that that was one way to ensure that one less obstruction to getting it into the standard was to have complexity guarantees. And it seemed to have worked because, as I said earlier, it's a large body of work, the STL, and it was gone through the standards committee, which are typically the standards committees. They're quite finicky about these sort of things. And it went through pretty quickly. It does help that it was supported by Strustrup and all the other guys in the standards committee. Main things that were removed were incidental to now, but interesting from a historical perspective. And the main way that STL and systems like it get their performance is by relying on static dispatch rather than runtime dispatch. And that means that a lot of the work is put into the compile time space rather than being left to be decided and implemented at runtime. People might have noticed that when you start using STL and start making complex data structures in STL that use the algorithms, your compile times go up to the point where if you use them in a very large degree, you might have to increase the heap space given to the compiler because the symbol tables get so large, and there's a lot of work being done at compile time. That work is there to make sure that the runtime is fast, so it's a good trade-off, in my opinion. That said, you've got to be aware that there is a compile time cost to using these techniques. And one of those costs is enforcing type safety throughout it, because, again, if you're doing statically type safe systems, you're putting a lot of the work that would usually be done at runtime, a lot of times doing it once at compile time. STL was originally attempted to be implemented using traditional loop design, where you've got a base container type and you've got a specialized container type that derives from that base type, changes its behavior according to what adding and removing means. Stefanov, after some trial and error, realized that that model doesn't work for what he was trying to achieve. Type safety provides better runtime performance, and on top of that, not only is it more performant, but it's more correct. At least it removes opportunities to fail. So complexity guarantees. All STL containers and algorithms provide complexity guarantees using so-called big O notation. I guess most people here are familiar with big O notation. Should have harkened back to your days at uni. Just rambled on a bit. A quick review, and for our intents and purposes, we'll only really need to worry about 3 or 4 different notations. Or one notation with 3 or 4 different uses. Constant time based on the number of elements under question, and time based on the logarithm of the number of elements under question, and so on. I mean, you'll get n squared. Complexity is another common one that I don't know many containers. Certainly algorithms will have those sort of complexities, but the containers, they're the most typical. It can also be constant, and as Kester pointed out, and I'll raise it going forward whenever I see that it's going to come up, but there's a constant in front of that log as well. So it's a constant cost plus a constant times the logarithmic of the number of elements. And if those constants are large and your n is small, then the constants can dominate your performance. One other catch is that a lot of containers provide amortized constant time, or they'll talk about amortized linear time. And this term amortized means that in general, I mean, it's got a more specific formal definition, but the take-home point is that when you see amortized preface, when they're talking about the complexity guarantee, they say amortized constant time means it's constant time in general, sometimes it'll be not constant. And that, you've got to be aware of that, because if you're running along and things are going great, and then you get a spike, and then you get another spike, those spikes are generally, that's what the reality of amortized means. You're going along, you're pushing back into a vector, it's all constant time because it's already been reserved, then you get to the end of the reserve list and it has to resize, and that's your spike. And that's what amortized means. So amortize does not mean always constant time. In practice it means generally this is constant time, but there'll be spikes. One reason why people were originally against STL, and the same guys were originally against C++, and the same guys were originally against virtual functions, and the same guys were... there isn't almost an unknown unless you're aware of it. So at first it was like, well, it can do all this stuff behind the screen, behind the scenes that we don't know about, and we need to have complete control. What we need to do as programmers in the 21st century is be aware of the issues so that we can still use it effectively without being scared of hidden gotchas. So understand what's going on and you won't be so afraid. One other good thing about complexity guarantees is not only can it'll give you a warm fuzzy feeling that you know that you're sorting a list in, or keeping a list sorted in constant time, or doing something else in a certain amount of complexity. If you yourself build up a system which uses other systems and have all got complexity guarantees, then your own system you can do this very simple analysis, very similar to error bar analysis to guarantee what complexity your entire system is by building that up, and then other people can. Of course that doesn't happen, but it's an ideal. But it is very reassuring to know. So we'll get on to the architecture of STL and how it's put together. There's a quote there, he wasn't trying to program in C++, he had an idea and he said that he got me ate bad fish, and he wants to express that. So he just wanted to find a good way to deal with software and software complexity. So the components of STL: iterators, containers, algorithms, functional. The interconnects between the components are created implicitly, as I said earlier, by the use of concepts and models. Iterator, fundamentally, is an object that specifies another object. There's a conceptual hierarchy of iterators, at the top of which C and C++ pointers are actually models of random access iterator. And this is a quite well-defined and non-trivial concept. I'll get into concepts in a moment, but people should understand that a C++ pointer is an iterator in the lingo of STL. And every time you see an iterator in STL or something requires an iterator, you can always use a C++ pointer. There's a concept hierarchy for iterators. Trivial iterators, forward iterators, reverse bidirectional and random iterators. I'll cover what these all mean shortly, but key point here is that the iterators are the bridge between containers and algorithms. So you can write the algorithm once and it'll work on different containers. The way that the algorithm can be itself independently without caring about the containers is that it's all the interconnects are via iterators. Now, a key point about containers in STL is that they take ownership of what you give them. So once you give an object to a container, the container then owns that object and you no longer are responsible for lifetime management of that object. Containers own what they store. Containers use value semantics. And we typically, historically, if we were going to make a container ourselves, then the first thing that we would do is to store a pointer to something that's kept externally, and we maintain a list of pointers or a container of pointers, and the lifetime management is outside of that container. What STL does is it gives all the ownership semantics into the container. So when you give something to a STL container, it owns it, it controls the lifetime of it. When you access elements in a container, you're given a reference to the value stored in the container. You're not given a pointer to something else, you're given an actual reference to the actual value that is stored in the actual container. And when you give values into the container, you pass it by reference. There are some consequences to this, which is that, there are a number of consequences to this. One of the most obvious ones, and one that people find most surprising, is that pop back on a sequence doesn't actually give you what was popped back. You've got to get what's at the end of the container first, then you pop it back. Now, the technical reason for that, I don't think we want to go into, but it's a consequence of the fact that the container owns what it stores. The simple explanation is that if the object has been removed in order to give it back to you, there's a point in time, if popback was to return a reference to the last thing, there's got to be a point in time in popback where it's taken it out of its container. And the problem with popback returning a reference is that where's it going to, that reference going to live when it's no longer in the container itself before it's given it to you. Another consequence of this is that when you shouldn't be using auto pointer anyway, and maybe you don't even know what it is, don't use standard auto pointers in STL containers. Assignment of one auto pointer to another changes the referent object. So when you say A equals B, typically that B doesn't change. All right? You're assigning from B to A. With auto pointers, B does change, and that screws with STL. So don't put auto pointers in containers. Use TR1 doesn't exist, especially to she. So don't use TR1 shared pointer. Don't use anything. Don't use anything. Don't put pointers. Shared pointers are the correct thing to use if you want to put pointers to objects in containers. Now, putting pointers, storing pointers in containers is a whole separate and a talk in and of itself, which I don't want to go into. The takeaway point here is that containers own what they store. There are consequences to that. Be careful when you store pointers in containers. I realise, I'm not stupid, I realise that everybody puts pointers in containers. Alright, that's just a common thing. I think we probably do that too much, and we could be saving ourselves a lot of trouble if we give the value lifetime management to the container instead of making an object, putting it in a container via a pointer, and then working with the container, and then we've got two levels of interaction going through that pointer, going through the container, through the pointer to get to the object, number one. Everyone's seen that ugly syntax, open parenthesis, star, header, close parenthesis, arrow, blah. That's two levels of interaction. You know, if you're doing that a lot, you could think about maybe putting the object in the container, and then you've only got one level of interaction and you don't have to worry about lifetime management. Another consequence of the fact that containers use value semantics to store their contained objects is that containers themselves are values. So you can make two vectors and you can compare them directly. Does this vector equal that vector? And that doesn't just say the same size, it actually compares all the elements, corresponding elements in the two vectors to make sure that they're all equivalent. So you can have vectors of lists of maps, a set of insta strings. There's one data structure, and you can compare whether those two things are the same thing.
Well, you wouldn't want to do that.
Can come in handy for things like input mappings and stuff like that. If you've got like an input key, you want to map to this and do these events, and I don't know, you can. Don't go too insane. Point being that once you've made this structure, the whole structure itself is then a value structure. You can pass it by value, you can return it by value, you can compare them by value. You can say if one structure is less than another one. Algorithms in STL take iterators as input and use iterators for output that divorces them from the containers that they're using to get input from and anything that you would store the output to. That is a, surprisingly enough perhaps, that is a STL container. It's a container with value type int that's been reserved with 9 elements. It's got a begin and an end. And we can fill that container using an STL algorithm fill, which takes a range to fill and a value to store. So we're storing from begin to end this value, and that will end up filling that sequence with the value 42 9 times. We can then transform that container from begin to end, writing the results back into the container itself and adding 3 to every element. Now, that's pretty obtuse, sort of not clear syntax, and it's just here as an example, I guess, of what not to do. But that is just a way that adds 3 to every number in that array, basically. Has anybody ever used or seen that sort of stuff before? Yeah, don't do it.
Okay.
But you can copy from that container. You can copy it to another iterator. Again, algorithms use iterators for input and output. In this case, the output is specified as a output stream iterator which outputs ints, which is given there, and the output stream that I will write those ints to is standard out. So basically that writes the contents to standard out. You can do a lot of other, I mean, I could fill pages with clever shit that you can do with this. I mean, that isn't the point, so I'm not going to focus on how clever can you be with STL and adapters and things. I just want to present it and talk about the architecture of it. The key point about algorithms is that the process of performing the operation that the algorithm describes is divorced from the storage via iterators. There's a lot in standard template library algorithms. I don't know if anybody's ever seen it. It's in the angle bracket algorithm header. It's got 90% of what you'd want to do from day to day is in STL algorithms, including set manipulation. So you can find, you've given 2 sequences, what are the elements that are common to both sequences, what are the elements that are disjoint in both sequences, what elements are in this and not in this one, and then find the unique elements in the remaining set. A lot of this stuff, once you start thinking about using STL algorithms in your own code design, what at first became, you consider it to be really complicated, but if you break it down into, okay, I need to do this and then this, like a pipeline, then everything just falls out into a couple of calls. You'd be surprised what you can do. The other thing that's in algorithm, and it's sort of hidden away, is there's heap management. That isn't memory heap management, there's a confluction. It's not memory heap management. That's basically heap management as it pertains to priority queues and heaps as a data structure. There's sequence operations and also permutations, so you can, given a range of elements, you can shuffle it to be a random permutation and find the next permutation, so it's a nice way to, you've got 52 cards, you can shuffle those cards in one step in STL, for example. So in general, if you need to do something either basic or clever, it's already been done correctly already, and the first place to look is STL. I'm not saying you should use it all the time for everything, but if whatever you need to do generally can be described as a sequence of algorithms. We don't really typically look at things that way, and maybe we could start looking at it like that a bit more, because then you formalise what you need to do, you've got complexity guarantees on how you do it. Functions, functional functors. STL provides a primitive means to deal with functors. I mean, I say primitive because when STL was written back in the early 90s, the idea of generic programming, template metaprogramming, functions, function adapters, functors, currying in C++ was quite alien, still is quite alien to a lot of people. So the first stab, I guess, that was done at doing this generically in C++ was in what I'm about to present, and it's quite primitive by today's standards. So there's functors in STL that create an object out of the idea of addition. So we've got plus with C+ operator in C++, A plus B. We can make an object that represents that operation. With those objects, we can do some funny things with them, like bind the first or second arguments. We can compose multiple function objects together to make f of g and g of f. Remember that from calculus days? And after all of that, we can pretty much ignore them. How they're implemented in STL is quite basic and difficult to use, as evidenced by the previous example, if you'll remember. I'm not going to bother. But the bind first, standard plus, int, blah, just to add a number as much as you write a loop would be everyone's typical response. It's generally correct. There are other libraries, quote unquote, that exist that do this and much more, much better. So don't use STL's function adapters and functional systems. I mean, you can, no one's saying don't, but don't. So what I rabbited on about earlier, and this is probably the hairiest, most abstract part of my talk, so see how we go, is I wanted to talk about the idea of concepts and models as it pertains to STL and as it changes your life. Concepts, and this is, I could have used I wish I could find a different word. We don't want to confuse, imagine this as being a whole new word you've never seen before, and don't confuse it with the actual word concept. Right? This is a new concept, which is sort of like concept, but it's like concept. It's a conceptual difference between concept and capital C concept. So capital C concepts describe both the syntax and semantics for usage of both types and instances. Now, there's no such thing that does this in C++. And this is where a lot of the meta in meta C++ comes in, and a lot of where people's eyes glaze over and they lose the plot, so try to stay with me. The key thing here is that it's both types and instances as well. So there's nothing else in C++ that unifies dealing with both types and instances. A given type is said to model a concept if it meets all requirements for that concept. So this is what a model is, and this is what a concept is. A concept is something that describes the usage of types and instances. A concept defines the boundaries, the explicit set of cases, within which anything that does this is a member of this concept. And a model is simply an actual C++ type that fulfills all requirements in that concept. The requirements may include whether or not a type can be default constructed. I'll be more precise. Whether or not an instance of a given type can be default constructed. Whether or not an instance of a given type has copy construction available to it. Whether it can be publicly destroyed. I don't know if you realise, but you can actually make the destructor for a type private, in which case only certain things, or itself, can actually have code that destroys that object. All of these things, including operators, equivalency, dereferencing, all of these things together go into making the concept. There's no way to define this in C++, but it's very important to understanding how STL and related systems work. So on top of these sort of requirements, there's also what you would say is more common requirements, which is, does the type have plus operator for it? Ints, for instance, have plus for them. A general structure that you make may or may not have plus operator for it. There are also other operations like dereference or even function call operator, which you can overload. And other requirements that goes into concepts include, does the concept have a requirement such that any models of this concept have nested types? So you could make a structure, you could make a concept which says that a given type must have a nested type called value type. And that means that if any model of that type has to have a nested type called value type. There's no way to enforce that, there's no way to write that down in C++. All you can do is you can write it down and press Ctrl F7. And it'll say, structure hasn't got type, value type. Then you know you failed, because you've got a compile error. You can't write down this concept, but you'll certainly find out when you get it wrong. So, concept is a set of usage patterns with associated semantics. Operations, methods, nested types. Now, this is where it can get confusing, but bear with me. Concepts themselves form a conceptual hierarchy. You've got an ontological framework of concepts, where you've got root concepts, and then you can have another concept which is what's called a refinement of a parent concept. So we're basically we're familiar with C++ object-oriented structure. You've got base class, derived class, which inherits functionality and member variables from the parent class. that extends it or changes default behavior. That's C++ standard OOP, right? Whatever. This is the same thing, but elevated up one level, where you've got a concept which describes usage of both types and instances, not just instances and not just types. And you can derive from one concept to another. So you can say, at the base of a hierarchy, you might have trivial iterator, which means an iterator is something which has got a dereference operator, which gives you a reference to what it points to. This trivial iterator has to do that, right? All iterators have to have a dereference operator. But then a refinement of that is a forward iterator, where you can say P++. And that means that if P is a trivial iterator, P++ goes to the next element in the sequence. So that is a refinement, and that's called a forward iterator, and that's a refinement of trivial iterator. And none of this is directly expressible in STL or any other form of C++ outside of other language models and the libraries that we won't talk about. But I will just quickly touch on C++ OX after this slide, I think. Concepts are ineffable and you can't write them down in C++. But models are certainly concrete things, because a model is a C++ type. And we say that a type is said to model a concept if it fulfills all the requirements for that concept. An example will make this clearer, I hope. So we have a structure here which its sole existence is to linearly interpolate between two values. It'll do that over whatever type of thing you give it. The alpha parameter to use, 0 to 1, how much to interpolate between those two things, is factored out as a scalar and it defaults to float. I hope that we're familiar with this sort of syntax. If not, you did in the order already. So we've got a structure here, construct it with a scalar, initialize it. We've got an operator overload, a function call overload, excuse me, which takes two value types and does the interpolation and returns it. Now when I say does the interpolation, this is the beast that does the interpolation. I hope I still remember how to do a linear interpolation. And there's some example usage. So we've got linear interpolate ints constructed with 0.5. Interpolate a three-dimensional vector by half. Assert that halfway between 2 and 4 is 3, and assert that halfway between 1, 2 and 3, and 3, 4 and 5 is 2, 3 and 4. That's not interesting. What is interesting is what are the requirements of T. And what we're about to do is to define the concept that T has to model. In this case, it'd be an interesting exercise for people to actually, excuse me, to try to figure out if they can see all the operators that are used. Obviously, we're adding two of these values together. We're also subtracting two of them. We're multiplying it by a scalar, which is that multiply there. And we're also, which is the hidden one, I guess, we're also doing an assignment operator, because we're returning the value of this by value. So we have to be able to copy that value, which can be surprising sometimes if you don't realise that there's an assignment operator being done here. If you've got pointers in these structures or you've got references in there, then the assignment won't work as you planned unless you do something special. In our case, we need to be also passing in by value, so you need to have an assignment operator for that as well. But these are the operators that we have to be able to use in order to have T as a model or to be used in this template. There's nothing fancy, there's no nested types, but there could be. In that case, that would also be listed here as a requirement in the concept. And again, you can't wrap all this up in the C++ and say, here's the requirements for the type T to be used in this. What we do instead is we press Ctrl F7 and see if the compiler works it all out or not. Now, that's all well and good, but it can also have some surprising outcomes, which is things can compile and not work the way you wish. And also, the compiler can make choices that can make it work when it shouldn't. People have seen that before, especially if you start doing operated casts, overload user casts and stuff like that. In any case, point being, here's the requirements for the concept that we use. C++ OX, there's only one slide on this, but this is what is coming up down the pipe for C++. It's been recognised that concepts are such an important part of C++ that they're going to be formalised into the language, and this is what it looks like. And I don't know if people know, C++ OX is the new standard C++ that was being worked on since late last century. It was supposed to be done sort of midway through the first decade of this century. They figured that OX would be enough, and they was going to substitute the X for the year it was going to be released. But we're now 2008. They're running out of X's. C++ OX point X, I don't know. Usually get hexadecimal, that'll fuck them. So in this case we can say that if we want to find the minimum of two things, we need to have less than comparable as a constraint on the type that we use. And in C++ OX you can make that explicit, so instead of just having the compiler barf at you, it'll politely point out that this T requires less than comparable. How that actually works.
That's really the key difference. There's just so much of the specification of the concepts and the models is
implicit.
It's implicit. And yeah, like you say, that's one of the things that is confusing about STL is in their documentation they have all the concepts and models listed out, but because they didn't have the language structure to be able to represent that other than through templates.
It's not written down in the text, so
and that's why it becomes confusing. This is basically just the evolution of that.
And you can actually, there's a new language construct in C++ OXX. Hopefully it'll come out 2009, but what does come out mean as well? It means Como's got a demo of it in their website, I don't know. So you say that there's a concept, not a class or a struct or a function, a concept called input iterator, which takes two types. And it requires that iter is regular, and that'll be defined as another concept. So it'll basically, then from here on it goes into pattern matching. So that has to be regular, which means, off the top of my memory, that it can be constructed, destructed, default, like it's a regular object, there's nothing special about it. Also that it can be dereferenced to get a value, which is passed in here. So given an iterator, you can dereference it to get the value. Given the iterator, it's got a prefix ++ to get to another iterator reference, and it's also given an iterator. Isn't it funny how things just stay there once they're there? This whole operator ++ int to specify a postfix increment as opposed to a prefix, which is operator ++. What a hack that was. History strip. And now it's already here in C++ OX, it's still here. This is the comma int, which is just a magic, it could be comma fucking spam. It's nothing to do with integers or int, it's just this placeholder to say that this is the ++ postfix and that's the prefix. So it's now pushed into C++ OX as well. Installing and linking STL, all modern compilers, it used to be a big deal. Which STL do you use? Do you use the Dinkenware one? Do you use this? Do you use that? All modern compilers come with STL and STL implementation, and they're generally all merged into one. Well, that's not true now, they've all diverged again. But some come with debugging. The safe STL, I guess people thought that it was unsafe at first because they didn't know how to use it. You know what I mean? Quite seriously, people were putting pointers in there and then erasing shit and then not wondering what's going on. So, oh, this is not safe. Better make a safe one. STL port is another one that was common for a while, but I think these days, unless, I don't know, if you've just been programming for the last couple of years, then you probably haven't, you've only ever used the STL that comes with Microsoft Visual C. The newer ones in 2005 have concept checking and, well, limited support for concept checking, and also there are debug configs for STL, Visual Studio 2005 and 8. that will also do things like ensure that if you give a less than operator for something, like you saw something using operator less than, it'll actually guarantee at compile time, at runtime, that it imposes strict weak ordering. So that if A is less than B implies that B is not less than A and all of that sort of stuff. So the implementation of STL, Bertrand Meyer said that correctness is clearly the prime quality. If a system does not do what it is supposed to do, then everything else about it does not matter at all. So, it's a quote, I guess, going into talking about the implementation. Some more good quotes from Stepanov. I realise that a parallel reduction algorithm is associated with a semi-group structure type. Now, all that really means, to me at least, is that he's focused on the operations that go into an algorithm. Like, if you've got a sort algorithm, you need to know if one thing is less than another. If you've got a plus, if you're doing an accumulation, you need to have the plus operator defined so you can add two things together. Associative binary operation is just you've got A less than B, B greater than A plus B. Again, it's just, to me, it points out how riveted he was, I guess, on how operations are the key thing, not the objects that they're operating on. The fundamental point, algorithms are defined on algebraic structures, such as, it took him another couple of years to realise that if you have to extend the notion of structure by adding complexity requirements to regular axioms, and that solves the problem of having too many answers. So once you say that this is a sort algorithm and it's got log n complexity on the input range, you can show me another sort algorithm. Has that got log n complexity? No, it's slightly worse. Well, I don't give it. It's whatever. You know, this is log n, and yours is that. Unless you can, you know, the point being that complexity guarantees provide a bottom. You know when you're finished, until someone else can come up with a better way to sort things. And he also had a firm belief that iterative theories were central to computer science. If you take that from an earlier point where I said that C++ pointers are iterators, it sort of follows. Every time he looked at an algorithm, he'd try to find a structure which is clearly on which it is defined. What he wanted to do was to describe the algorithms generically. Has anybody ever actually looked at the algorithms in STL? No one's looked at the source code.
Seen it.
It's pretty scary, and that's a general response. But the guy who wrote those algorithms didn't write it in the way that you currently see them. He wrote them in a human way, and they had comments, and they had proper variable names, and it was properly structured and formatted. I can guarantee you, no one can write that the way you see it. The reason it looks so scary, and this is an important point, because it isn't all magic weird shit. It looks the way it does for a number of technical reasons. It's got to use underscores for all globally seen variables so it doesn't clash with your defines, right? It also means don't put an underscore in front of your define, or you can clash with standard things. But that's why there's underscores everywhere. It's just a standard requirement. This is why the C++ has a rule that users can't have underscore in front of all their symbols. That's reserved. That's why there's underscores in all the standard libraries. And also, because it was known that these headers were going to get compiled a lot in frequency, they had to be made to parse quickly, which means limited formatting, very short variable names. So you end up with underscore x, underscore f, less than, bad formatting, no comments. You know, if you actually took the time to break it out, give it some proper names, give it some proper formatting, it's not as bad as it looks.
Microsoft's current versions seem to have, they're a bit more intelligible. So
Right.
I don't know, maybe these are compiled or something, but the last time I remember plugging some STL on Windows PC was sort of like,
It wasn't quite so
you can't
bad.
understand what the hell this means.
If you just, like I said, if you just get a block of code and search a place for input for underscore x, and just, you can start to see what's going on. But yeah, that's why it's so difficult to read. I've lost my point. What was I talking about here? Quotes. Implementation. Iterators. Iterators are the logical buffer between containers and algorithms. It's a way for different systems, just to press home a point, it's a way for different systems that otherwise are disparative Marcel doesn't have to know what Vladimir speaks, but they can communicate via someone, an intermediary who knows both. And that's where iterators sit in the middle between Marcel and Vladimir. So you've got algorithms, containers, iterators. Algorithms have minimal iterator requirements, not minimal container requirements. So we've got trivial iterators, which require that you can dereference it, and equivalency for 2 iterators. That's all you need. If you've got that, then you can say that this type models trivial iterator concept. You've got forward reverse iterators, which have got 4 different usage patterns on top of trivial. This concept is a refinement of that concept, so this already requires everything that this concept requires. On top of that, it requires that you've got plus plus p, minus minus b, p plus plus, p minus minus. And it also describes what those things mean. So not only do you have to have plus plus p and minus minus p, it's also a requirement of the concept that plus plus p goes to the next element in the sequence designated by that iterator. Right? So it's not just that it can do plus plus p, it also means that when you do that, it goes to the next element. Again, it's not something that you can write down in C++, it's a semantic. But there are also bidirectional iterators and random access iterators. Bidirectional is a refinement of either one of these, I guess, in which is both of those together. And random access is your C++ pointer. Surprising that this is so complex, isn't it? This thing, all C++ pointers are trivial. And there's also other more convoluted requirements, such that star plus plus p, we know that as being give me what is pointed to by the result of pre-incrementing p. And we treat that as being 2 operations. But as a concept, all we need to care about is that that expression, star plus plus p, gives me what's pointed to by the next element in the sequence pointed to by p. Iterators are implemented using a type traits system. I guess people are familiar with the idea of type traits?
I think you should cover it.
Okay. Type traits provides a mean, it's basically a pattern matching system which enables you to do various levels of conditional compilation. So you do a compile time dispatch. You can do almost something similar to if then. If anybody's used language systems like Haskell, or that does pattern matching for arguments. So you have one function with many different argument signatures. We're familiar with this in C++. Similar to that, where it'll match up what you give it as a type, and it'll try to match that to a given structure. So iterator implementation for copy, well, I should say the implementation of copy algorithm takes iterators. So it's got an input iterator to specify the input range, and we've got an output iterator to specify where to put the output. Now, what happens in STL when you press Control F7 effectively is that the compiler will do a static dispatch on the types of things that you pass in to figure out how to generate the code, and then use that to actually generate the code given the actual instances that you've passed in. So the take-home point here is that the types that are actually used on the call that you've made to copy, those types are fed as input into a system, which then goes away and does work at compile time to generate the code to actually perform the copy. So the actual code itself is determined when you make the call at the point of the call. It isn't predetermined. And in general, on a good implementation, copying from a standard vector int to a C-style array will resolve down to a simple mem copy. It won't do a for loop, copy in, copy in, copy in, copy in. A good implementation will know that it's taking an int pointer and an int pointer as input, and it's writing to an int pointer. It'll use type traits to determine at compile time that what it needs to do is a mem copy. That said, it'll still do other things. If you give it much more complicated structures, you could copy from one container of containers to another container of containers and write the results to standard out, for instance. It'll still go through the same type trait system to generate code that does it correctly. And again, disconnect between algorithms and containers provided by iterators. ++ P or P++. There is a difference. We all know what the differences are, right? If we have, and this is just to make the case that you should always use ++ P, unless you've got a good reason not to. If we have a foo and we want to have both pre and post, we've got to use this weird screw strip design. I ate too much bad fish at the moment where he decided that he had to use an int there to specify postfix. If we use prefix, which is the preferred way, then we can return a reference. We can pretend that there's an int num in this structure. Then we can pre-increment our number and return a reference to this, and we're done. If we use post increment, we can't return a reference, and instead we have to make a temporary copy of what we currently are, then increment ourselves using the pre-increment, and then return the temporary value via value semantics. This is more expensive than this. This is a trivial case, obviously, but some iterators are non-trivial, and in which case it's much better to pass them back by reference if they're bigger than 4 bytes, which a lot of iterators are. Well, an iterator can be. Then it won't go back in a register. You should always prefer to use ++ P instead of P++. The restream iterators provides a means to deal with input and output similar to iterators. So we've got standard O-stream iterator type given an O-stream. This is just, we don't really use streams very much at She. This is a way which enables you to iterate over a stream, or for input, or to iterate into a stream to write results as output. So this is a way to write, this constructs an object which, when assigned to, will write a T into a given O-stream that's stored as reference. There's a couple of examples of this coming up in Fred. The end of file is specified by a default constructor. And when you assign to an output stream, it inserts into the stream that it stores. When you when you dereference so on assign, this will insert. On dereference an iStream, it'll extract. And dereference does nothing for output iterators. Populators, they smell like the stream adapters. There's also populators, which are also a form of iterator, but instead of specifying a range in an existing container, they add objects to containers. So we've got standard back inserter, and when you pass one of these as an iterator, as an output iterator, instead of writing it to a result, it'll add it to a container that you specify as an argument. Back inserter. So standard back inserter is a populator that appends to the end of the container. It calls pushback on whatever it is assigned to. So here we've just got a Here's our STL container. It's a string literal. The beginning of that container is pointed to the H, and the end of that container is a point to the null terminator. So the begin is just that's what we consider that to be the string literal, and the end is at the start, well that should be begin, and equals begin plus 6. So then we've got our range, which is begin and end. We've got an array of chars, which we're going to call our string. And then we can, this is a very convoluted way of creating a string, but we can, that should be copy, not fill, my apologies. Copy from the beginning of that string to the end of that string into a back inserter into this string. So that every time we go through this loop, I apologise, that should be copy. Standard copy, begin and back insert a string. That will copy, go through this container of chars, which is represented as a string literal in C++, and call back in, push back on this vector. And it'll end up at the end of this with the string begin to string end, which is this range, the full range of this container, is equivalent to this container represented by that string literal. We also have, in a similar way to back inserter, we've got inserter, which instead of calling push back, it calls insert. So we have a set of strings. I apologise for all the STDs, but not sexually transmitted diseases. I mean, wanted to make clear what is and isn't part of the standard. By the way, just as an aside, string is not actually part of STL. It's part of standard C++. It's in the same namespace as STL, but it's not actually part of STL. Which is a very wise move from stepping on. So here we've got a set of strings. I'll explain set in a moment. We can copy using our iStream iterators. I hope this is, maybe if you flip through effective STL, you've seen this before. I just want to give an example of how you'd use inserter. Copy from the input stream represented by CN, pull out standard strings until you reach the end of that range specified by this argument, which is an iStream iterator, a standard string which is constructed with nothing. So this represents end of file for all inputs strings that take strings. You can use the same thing for any other input string that takes strings. And so that's the input range. So copy from this to that into here. And what this is it's a function object used wherever you can use an output iterator. When that gets assigned to, it'll actually insert what it's being assigned into, it'll insert that into this container. And you'll end up after this with a set of strings that have been read from standard in. As a side effect, and this is a sort of hateful thing which has been addressed in TR1, set is ordered. So you won't only get a set of strings, you'll get an ordered set of strings. Not only that, it'll be an ordered set of strings where each element is unique. So if you had the quick brown fox, the result of that will just be the quick brown fox. Type traits use a simple pattern matching. I guess I won't go too much into this. I just wanted to give a concrete example of how that, what I mentioned before about static dispatch, how it decides what to do given type arguments. We have a structure here called isInt, and this is standard practice for how to nest a value and use it at compile time. So you think of this as a compile time int almost, but it's just, what we're saying here is, here's a meta function, if you like. It returns its value here, and it takes as input this type. When you call this function at compile time, you pass in a type, and it'll store its result in here. And this is the signature for our meta function. And then we say this function, when given an int as input, its enumeration, but its return value is true, 1. So this will mean that by default, the return value is 0. When you give it a type int, then its value is 1. And what it's saying is, yes, this is an int, because that's an int, and that's an int, and that's 1, and that's 1, and it's not an int. Anything else is going to give you 0. So then you can say static assert, this doesn't exist. I think there is another static assert, I should have found out what it was, but there's a mab static assert, I think. If there isn't, there should be. And that's, so you can say, you can assert that at compile time, our meta function correctly states that short is not an int. So assert that not is in short, but you can also make sure that it's true by saying that is in int. We know that that's true because we can just see struct int is int new value 1, so that's going to be right. I went into some detail there to say that this is using this technique and similar techniques. You can build up what's called meta programming systems, where you make compile time decisions on how to do what's called type synthesis, where you're building up types at compile time to match most correctly the inputs that you give. Why do we need it if it's static? It's to make sure that we can generate efficient code to deal with our copy example, and that will use a system similar to this, where it will switch at compile time to do different things depending on the types that are given to it. This can get quite complicated and actually much more interesting than C++ alone. I mean, if you look at this just as a very tortuous way of writing a C++ function, it's pretty fair on the mark. I mean, it's also clear that we're hacking around the fact that we haven't got proper static or compile time variables. Instead of compile time variables, we're using enumeration values, and just the fact that you can initialize them happen to give us a way to assign values into those enumeration variables to give us, and then from that we've built up basically a programming system at compile time, which is generally tortuous and hard to read because it's not what the language is made to do. But it does give you some things that C++ can't do, which is things like pattern matching argument types. And we've got argument traits, which is something which is sort of missing in STL. A lot of compilers couldn't do this for a long time, and it meant that they couldn't do a lot of things that we can now do. And if STL is going to be written again, to be written in a much more efficient way. There are efficiencies in STL, I probably shouldn't say that out loud. It's not always the best of best that you could possibly ever do, irrespective of anything. And the reasons that it's not the best that you could possibly do in all cases is because they didn't. One of the reasons is that they couldn't do template partial specialization, which is what this is, which is how you would say, how you would properly deal with references, const references, and value types, which STL doesn't do. For instance, you can't have a vector of references. Not that you could. Well, you sort of could. Anyway. If you're going to do a vector of references, then you'd have to do something like this, where you say that here's an argument, and you want to know here's the type of thing. What sort of type should I use if I was going to pass this as an argument to something? In the default case, which is this first case, given a type T, you should pass it as a const reference, as an argument. So you say argument, int, well, int's not a good example because you should pass ints as ints and not as const references. But argument of a foo, you should always pass foo as an argument as a const foo reference. However, you can't always do this, because if T itself was a reference type, then you'd have T reference const reference. You can't have a const reference or a reference. It doesn't make any sense. So the argument type, for the case where, for any type, but where that type matches this pattern, then you should use this. And what this is saying is, if the type passed in matches this T reference, then you should pass it as reference. So then argument of type reference should be passed as reference. And an argument of type const reference should be passed as const reference. So this is a way, this sort of, I won't go into more detail on where, how, or why, but this and type traits together, pattern matching types against and specializing on types, along with type traits to switch through where to go at each branching. They're the two mechanisms that are used. An example of containers, you can add ints to them, and I wanted to make the case here that you can't do that because you can't make instances of type void. So, of course, containers take arguments, but because containers are value types, containers themselves can be used as elements to be stored in another container, so you can have vectors of lists of ints, in which case you can access the first one using index operator. You can go berserk if you want. I guess Tyrone would yell at you if you went too berserk. So you can have maps of strings to sets, etc. and so on. Just some simple advice, and I guess it's clear to anybody, is if you find yourself needing this sort of a map of something to something else, and that second thing is a type itself, you should always type def it out. So you type def the first thing out to something, so I'll type def that out to a set of foo called foo set, and then have a map of a string to foo set. It's much clearer. And do other various things, copying again from standard in. That's just copies ints from standard in to standard out, standard error, for example. We're getting there. Containers, standard containers, list, vector, map, set. I guess we all know those. I'm not going to go into too much detail. Adapters, sets, stacks and queues, and decks. As I've been rabbiting on about, containers take ownership of the instances. Lifetime management is controlled by adding and removing values from containers. You don't control the lifetime of objects that you store in containers. What that also means is that if you look at it another way, it's a good thing. I mean, it is a good thing. You don't have to do lifetime management for the objects. Once it's in the container, it will stay there, it will exist until you explicitly erase it from the container. You can treat the container itself then almost like a heap. It's your own private storage of objects. You can add objects to it. They'll always exist until you remove it from it. If you find yourself putting pointers into containers everywhere, just ask yourself, do I really need to store pointers to things in this container, or can I just put the values into the container itself? Contiguosity. Yes, I can make up words as I go. That isn't a word at all, but I'm just referring to one of the key characteristics, as I see it, between different containers is the storage that they use contiguous in memory or not. You know, what's the difference between a list and a vector? Well, the primary difference to me is that vector stores their elements in a contiguous chunk of memory, whereas list uses nodes and they're all scattered over the heap. So list, set, and map are all node-based, non-contiguous containers, whereas vector and deck, by default, because you can change the container used by a deck. I think deck defaults to vector, am I correct? Or is it list? I think deck defaults to vector as an underlying container. Vector, sorry?
Table?
Table, unordered sets, unordered maps, hash tables.
Is that a new addition?
I added it 20 minutes before I gave this talk. What I actually mean is by table, I mean hash table. So you've got vectors, decks, hash sets, hash maps, and also unordered sets and unordered maps. They're all tables. They're contiguous in memory, but tables are sparse. So I'm going to skip through this quickly because hopefully this is largely familiar territory for people, and I've got a summary at the end. We've got a doubly linked list. Sidhe Graphics also has a singly linked list called S-list. They've also got rope and a few other things, which are stronger strings, believe it or not. Lists have got constant time insertion and removal, slow to sort. I meant to fix this. I think it uses bubble sort list, if everybody knows bubble sort, right? It compares two things. If one's less than, if the top one's left, then it swaps them, otherwise it leaves it, and it just does that, so the list is sorted.
They don't only use sort algorithms that, well, can't use sort algorithms that use random access.
That's right, it's only got forward iterator. In fact, the best way to sort a list, don't use standard sort at all. There's a list dot sort. It's a member of list itself. Unlike vector hasn't got a member called sort, list has a member called sort, and what it does is it uses the fact that it's a list to make a very fast, or to make a fast list sort. So even though you can say, given a list, sort, list begin, list end, that would work, I think. Yes, it would. Maybe. I'm not even sure that sort has an implementation that just uses forward and reverse iterators. Fail. But there is a member-wise sort. The reason I don't know that I've never done it because I've always known that there's a dot sort on lists and you should always use that. So that uses a custom algorithm for lists. It's got to access the nth element in a list, you need to actually go through all the previous elements in that list. Hopefully this is all pretty standard stuff. One good thing about lists is you can add as many elements to it as you need, as you want, and it'll never actually resize. So it's constant time addition to the end. It's not amortized constant time, it is actually constant time.
But we generally don't tend to use lists because they're fragmented.
Yep. But we haven't got a memory allocated with fragments, so do we?
I don't know, tell me, Lloyd.
You would use a list when you want to insert and remove from an arbitrary location in a container. Now, lists are good if you want to maintain where the order of matters and the order changes, and the order changes on somewhere other than the end. So if you want to keep a list of things, like, you know, list of players in some sequence, and you've got 32 players, and you might use a list. I don't know. That's the wrong example. But Tomo's right, you wouldn't generally, I mean, by default you'd use a vector, which is a dynamic array with a C-style interface. It's got slow to insert and remove from anywhere other than the back. So adding to the back of a list is constant time, but inserting into the middle of a list, you've got to shuffle all those other elements forward, one, and copy into the new spot. But you've got constant time access to any element in a list. Via an index operator, it's slow to insert and remove except from the end. And you should use vector as a default container. If you just need to store some place to put something, then use a vector by default. And if you can't use a vector, you can probably use one of the associative containers like map, which maps from a key type to a value type. For instance, map of string to function handler, a map of number to object. Every implementation I've seen of map uses a red-black binary tree underlying. You might remember those. They're sort of like AVL trees, but not really at all. The thing about trees is, you know, they're great. Trees was an interesting choice, by the way. I mean, you're not supposed to know that it's based on trees, but every STL implementation I've seen of maps and set uses trees. There's an X tree header. Have you seen that? You probably had a crash somewhere and it's, oh my god, what the fuck is X tree? X tree is the base data structure that is used by both set and map. So set is just a map where both the key and the value are the same thing, but they both use the same type, which is a red-black binary tree. Which are great. Red-black binary trees are fine and all well and good, but they can fragment memory because they're node-based. Also, logarithmic time is fast. You've got 1,000 things. How many, you know, what's logarithmic? You know, that's what, 3.5 or something? On average, things to find one thing out of 1,000 if you've got logarithmic time. That's fast, but if you've got 20,000, you know, it's 7, and if those comparisons need to be really super fast, the logarithmic time is still not a constant time. So let's not get carried away with our wonderful logarithmic time is. It still is better than constant, worse than constant time.
So, just to confirm that unordered set and unordered map now exists? Because we talked about it the other day, but
Yeah, I don't think I can quickly come.
but they will be.
They will be.
And they'll be preferred to standard map.
I'll just speak a little bit about unordered set and unordered map. And there's a table at the end which will summarise all of this. People may not realise that set and map are ordered. So when you add things into a set, it's not only a collection of things, it's actually ordered, which is doing extra work possibly than you really need to care about. All you really want is a set of things. You want it to be unique, you want to have fast lookup on whether or not this object exists in it. But you don't really need them to be ordered. So you've got constraints there. It has to have an operator less there to go into a set, for instance. It just has to. There's no other way. You can't put it. It's a requirement on the concept used by set that any type that you give it has to have operator less than defined. Not only that, it has to be strictly ordering. Whereas unordered sets don't have the requirement that T has to have operator less than. They do have to have operator equivalent to, otherwise you can't tell whether something exists or something is found. But it doesn't have operator less than, it uses operator equals, equals. And it's based on the underlying structure here is a hash table, not a binary tree. Now, everybody knows that hash tables have got better lookup performance than a binary tree, right? In general. As long as you've got a good hash function and you've got the right hash size and all of that, it's not a simple blanket statement. I wouldn't dare say that across the board, but in general, if it's a well-maintained and consistent system, then a hash table is better than a binary tree. Also assuming that you've got the extra memory to store the hash table with a lot of caveats, but shut up, Christian. So we have / will introduce this structure to map, which is a set of things that you can use for constant time insertion, constant time lookup. That's not logarithmic time insertion or logarithmic time lookup, it's constant time insertion, constant time lookup. I'll paraphrase that. Amortized constant time. Same for map. And maps have logarithmic time insertion and removal and log n lookups. There's a summary of this coming shortly. We've got a set. A set is a map where the key is the same as the value. Uses the same base structure as the map. Use it to store a collection, an ordered collection of unique objects. Log n, insertion, removal, and lookup. You also have multiset and multimap. Has anyone ever used a multiset or a multimap? Yeah. Yeah. They're not so common, I guess, to use. So a multimap allows one key to map to many values, whereas a map will always only map one key to one value. A multiset allows many entries with the same value, whereas a set will only allow one value to exist in the set at any given time. I say limited use, that's completely arbitrary, unfair of me, ignore that. But I've just never had too much of a use for it, but it's a stupid thing to say. It's like saying that, I don't know, it's just a stupid thing. Comparison of containers. So, I mean, this chart could also be this big and have a lot of other rows and a lot of other columns. And so, it's not an exhaustive comparison of the different data structures, but it gives you an idea. And like I said, there's caveats to here, and if I read this, I'd see a lot of oh yeah buts, but I got sick of putting little asterisks everywhere. So this is just a general thing. Please point out if I'm really wrong somewhere, but...
I guess the one thing we just want to add to that is the memory fragmentation characteristics. So you just talk about the memory size requirements.
So we've got the contiguosity, which is, are they contiguous in memory or not? The ones that are contiguous in memory here are vector and table. Again, table is a term that I'm just using to describe everything that's based on hash table or unordered. As Craig pointed out, it's just a word I've made up, but to me it makes sense. You've got lists, vectors, maps, and tables. You know that maps are tree-based and tables are table-based. This is contiguous in memory. This is contiguous in memory. The other ones, that's node-based, that's node-based. That could be either depending on the underlying container. Typically it'd be a vector, in that case it's contiguous. So lists insert on average anywhere in the container. That should sort of mean I found the terminology here to be confusing and also trying to fit into my headers without screwing up my table sign. So inserting anywhere into a list is constant time. Is how you read this. Erasing anywhere from a list, constant time. Erasing or adding to the front, constant time. Erasing or adding to the back, constant time. Looking up an object in a list is going to be n. You've got 12 elements in a list. You want to know whether a given element exists in that list, you have to go through all 12 elements. Construction time. This is like how complex is it to construct the object. It sort of matters a lot if you're constructing it on the stack and you want to use it for just a small little bit of things and then let it go, then the construction time matters. For a list, it's 0. Well, it's not 0, but it's very small. All it needs to do is initialize 1 pointer, I think. 2 pointers. Some implementations of list will actually create what's called a sentinel node. So the construction time in that case is a bit more than small. It actually buys a node to start with to use as a sentinel node. It's a detail, but some implementations will do that. In general, it's quite small. The memory overhead for a list is small, and the iterator type is forward/reverse. It's not a random access iterator. For vectors, on average, I've used n on 2 here because if you add into the middle of a list, you need to copy half of the vector forward and then copy into it. It's a bit of I tossed up whether to have n or n on 2, but if you add into the front of a list, obviously you've got to copy all of those elements forward 1 and copy into the front. In that case, it's n. But if you add into the back of a list, then you only have to copy whatever's left and then copy into that. So I've just said n on 2 as average. Erase on average is n on 2. Erase at the front is always going to be n, because you always have to shuffle all the objects down one, so that's very expensive to use to pop the front of a list. Or add to the front of the list. But adding and erasing to the back of a vector, sorry, search for what I said and replace what I just said with vector. Adding or removing from the end of a vector is constant time. Looking up into a vector is, well, now see, I've now done the wrong thing, haven't I? Because accessing the nth element is constant time, and it's constant time there, but I originally said that finding an element in a list is n, in which case finding an element in a vector is also n. So, I apologise, but this really means finding the nth element in the container. Construction time is effectively 0 for a vector. It's just got to initialize the pointer. Memory overhead for a vector is 0. Memory overhead for a list is negligible. You need every node that you allocate has to have a forward and back pointer in that node as well as your value type. So you've got 8 bytes of overhead per element in a list, whereas for a vector you've got no overhead per element in a vector. And the iterator type for vectors is random. Decks are very much like default decks are very much like vectors, except they're constant time at the front as well as constant time at the back. Trees, by that I mean sets and maps. Logarithmic time for all operations. They've got a small construction cost, very similar to the list construction. I mean, a list is just a degenerative tree, and they're very similar internally. So all it needs is a node, and just needs to do nothing to do it, to construct it. Like a list, it's only got a left, right, and parent pointers. Not much, and iterator types forward. But for tables, which are the unordered sets and unordered maps that you'll all start using, I hope, correctly and at the right times. You've got constant time, insert, constant time, erase. And constant time, lookup. they're unordered. I mean, you can, well, I say not applicable, and I originally had ones in there, but they're unordered, so unless you already know what's in there and why, you don't really go around inserting and removing you don't insert into the front of a hash table, right? You don't pop the back of a hash table. That isn't really how you use it. It doesn't make any sense. So I just say these are not applicable. The thing that are good about tables compared to everything else here, this is constant, constant, constant. This is constant, constant, and this is N on 2 or bad performance and 1. These are all logs. That's great, but even better yet is 1, 1, and 1. On the downside, our construction times for tables is quite large because we're constructing a hash table, which means we need to make some sort of bucket list to start with, and you know it's a large chunk of machinery which you don't want to be making on the stack. Generally, the memory overhead for a table is large compared to everything else. The memory overhead for a tree is just 2 pointers per element. Overhead for a table, we've got a big table that's sparsely filled, followed by a set of lists. So it's not, they're a bulky structure that happen to have the best performance characteristics. It's always a trade-off, right?
What happens when the table runs out of
resource at the table.
Right, so that could be quite a massive.
More time is constant time. You can set policies on these as well, and we'll come up to the best practices. I mean, a lot of hash table construction and management, determining the initial size of the hash table and how it grows and the hash function, magic is still voodoo. There's no blanket answer to it into how to deal with that. It's case by case.
I guess the thing is we're going to be adding this table to the wiki somewhere, so we use it as a reference point for people. And like I said, we'll be adding the fragmentation characteristics as well, plus also the specific containers like, you know, the map unordered sets and the map hash maps or hash indexes and stuff like that. So.
Yep. And in map core, as Tom was just saying, there's the map containers which derive from the STL containers and use hard-coded map-mem allocators. So you've got map list, map vector, map, map set, and map unordered set, map unordered map. And you should use these in production code rather than std list, std vector, primarily because you won't have to turn on or off or do any work to get MadMem debug database and also the defragmentation heap. Adapters are interfaces to other containers which provide different or limited functionality. For example, the standard stack container which is available to you to use is not actually itself a container. It's an adapter on another container. The default implementation in STL is to say you've got a stack of type T objects. The actual container to use is passed in as a template parameter, and it defaults to being a deck. Now, I don't know why it defaults to a deck. There's a good argument to say it should default to a vector, because you never add or remove from the front of the stack. You only ever work at the back. That should be a fucking vector. It isn't. It isn't a vector, it's a deck. I don't know why, but it is.
Needs a patch, Chris.
What an adapter does, what the stack adapter does is it allows you to treat any given container as it was just a stack. It limits what you can do with it, basically. You can't iterate over it, and you can't insert into the middle of it. All you can do is push back and pop back, which I find frustrating. I've never used it when I realised you can't iterate over the contents. I've never used it since. But yes, and it is true that decks are also an adapter which uses vectors, but it's an aside. I don't know why they didn't just go and stack them. Common methods for containers is empty. It's a lowercase e. Hate me or hate PowerPoint, which uppercases every first letter to you. That's const as well, and it returns true if the container has some elements. Don't use size to determine whether or not a container is empty. Size in some containers is, in general, I've got order of question mark. There's no requirement on the complexity of size for a container or for a sequence or an associative container. But an implementation is free to say if you want to find the size of a list, it will have to count through every element of that list and then give you the size. So if you want to know if the list is empty and you've got a list of 4,000 items, it's going to count through every 4,000 objects just to tell you that there's not 0 objects. And in that case, empty is much better to use. Clear, again, the complexity of clear is container specific, if you like. It removes all elements in the container. Don't use erase begin end, although you could. It's a bit more efficient to use clear. I don't want to get into a big discussion about assign methods and how to trim a vector and how to clear a vector and make sure that the vector's actually got no storage left if you assign a null vector to it and swapping with a null vector and all of that. There's a lot of detail, and I mean, for that sort of detail, I suggest you read Effective STL, Scott Meyer, and that sort of stuff. I'm just giving a broad overview of the common methods that are in containers. There are a lot of gotchas with memory management, even to do with vectors. Obviously, you've got begin end, and you've got const and non-const versions which do matter. I don't know what the heading was for this whole section. I think it was implementation of algorithms. The implementation is pretty much just basic computer science. When I say basic, I mean there's nothing fancy about it. It's just here is quicksort, here is radial sort, here is, priority queues, here is this. It's all just basic Dijkstra type stuff. There's nothing magic about it, except, like I said before, it's been obfuscated on purpose to make sure it's standards compliant and that it parses quickly. Passes quickly for computers. Some interesting reading in the algorithm headers, but you need to reformat it and do simple renaming. Common algorithms, I mean, you can argue that min and maximum are algorithms, but it takes 2 arguments as input, it does some work and returns one of them, so it's an algorithm. We'd all probably should hate correctly Microsoft for using preprocessor to define lowercase min and lowercase max. Yeah. What can I say? Copy for each. One thing about for each, what it does is it takes a range and it applies a functor to all elements in that range. So you could say for each element, do this thing to it. It's not commonly known, but for each should be immutable for technical reasons. For each, you can certainly modify elements, for each loop. But you generally, I mean, the standard is, I should say, that when you use for each, you go for each begin end, do this. What it does shouldn't change what it's referring to. For that, you should use transform, which transforms a range to an output given the function. Accumulate, find the minimum in a sequence, find the maximum in a sequence, and priority queue work. The priority queues, still don't understand why STL decided to expose a priority queue as a set of algorithms and not as an adapter on a container or something. But I don't know if anyone's ever done things like iterative deepening A-star algorithms or stuff like that for search trees. Then you need to keep priority queues. You can basically do A-star in STL in like half a page of code. It's already got everything you need in there to do a nice A-star. It's just that the priority queue is all hidden in these heap algorithms. Don't ask me why they did that. It really should have just been, here's a priority queue, and treat it like a stack. It takes something as a container to use as its underlying data structure. They could have done something like that for priority queue. If you ever need a priority queue, just know, oh, Christian said something about priority queues in STL. Then have a look at the heap functions in the algorithm. The functional stuff, we've got the functors, unary function, binary function, These are structures which enforce, or which supply a framework for embedding the return type as a nested type. Remember I said before that concepts can have a lot of things in them, including a requirement that any model that is used in this, for this concept has to have a nested type. In this case, the unary function has a nested type called return type, and it's got a nested type called first argument type. It's actually just called argument type. And then for binary functions, it's got a nested type, return type, and a nested type, first argument type, second argument type. Again, there are other libraries that do all this much better. Don't bother too much with this. Hard to read, hard to write, and hard to debug. I was sort of familiar with it, so it's just there, but I don't recommend really doing it. And there's some stuff there. Now, I hope that you would give me some leeway to sort of just tidy this up. I apologise, it's slack, but I've been sort of flat out and I haven't completed this document. It is there and it does exist, but
There's a folder we should be putting that on the server as well.
yeah, so I'll follow up on that shortly. There certainly is stuff to do, and hopefully some of you will find it interesting, or more than some people will find it interesting. Some resources, effective STL. This is pretty much, that's what you would more expect, I guess, from a typical STL talk. There's some very interesting reading. I really recommend that you start with that.
There's another place that will be housing some of that stuff as well.
I did ask around and that's what I found, but yeah, I need to sort that out. There's STL filter, which is a deobfuscator for STL messages for all common compilers. So if you ever get a really weird, wacky STL message, or you can actually set it up so that it'll parse the output automatically and give you a half-decent compiler warning.
Is it just for Microsoft or it
All
works on-
compilers, 360 going back, Como, MetroWorks, all compilers. Your Dove systems, they're a collection of C++ libraries building foundational technology to allow the construction of commercial applications by assembling generic algorithms through declarative descriptions and updates nothing. It's just good reading, I guess, an offhand of good reading. And that's, again, this is where Stepanov now resides. So that's what he's been doing recently. And if you're mad keen, there's some papers and interviews and another interview and SEO-based multi-threaded library from Alexander Stepanov. Oh, inspired by an article from Stepanov. Just reading, and coverage of Stepanov and the source code. I think that's it. Any questions? I don't know, or any comments, questions? Nothing much? Okay, cool. I'll follow up with a